Hi everyone, I'm Xinrui from the University of North Carolina at Chapel Hill, and today I'm presenting my work on longitudinally consistent individualized prediction of infant cortical morphological development. Neurodevelopment is exceptionally dynamic and critical during early postnatal period, as many neurodevelopmental disorders emerge from abnormal brain development during this stage. The modeling and prediction of individualized development is essential to understand the early developmental patterns in health and disease. The discrepancy between the real and predicted cortical surface could be considered as an index of a deviation from the normal developmental trajectory and may infer potential biomarkers for abnormal brain development. The prediction of typical development might be useful for data augmentation in training other foundation models. Although many efforts have been proposed for individualized predictions, such as conventional regression models or deep learning methods, they have two major drawbacks. Regression models suffer from the strict data requirements, which require data as on specific ages, such as 6 or 9 months. However, predict development as on specific age is impractical in many scenarios and applications. While some deep learning methods could flexibly predict development at multiple ages, however, they predict the missing data independently. For example, for an individual, we have the cortical surface at 6 months, and we can get a prediction cortical surface at 10 months. And based on another cortical surface at 18 months, we could also get a prediction at 10 months. There must be an inconsistency between two predictions due to the model errors. But most important reason is that predicting independently ignores the intrinsic relationship, such as the temporal consistency between longitudinal scans. So what we want to realize is that for an infant who has two available scans from his birth to 2 years, based on his first available scan, which is the blue one, we could obtain his complete developmental trajectory. And based on his second available scan, which is the red one, we could obtain another developmental trajectory. And these two trajectories should be as similar as possible. To summarize, our goals are to develop a flexible framework for individualized prediction of full developmental trajectory, and to reinforce the longitudinal consistency of different inputs to increase the ambiguity in practical scenarios. Therefore, we propose a flexible framework, namely longitudinally consistent AAA disentangled autoencoder. The architecture of proposed framework consists of an encoder, which extracts input cortical surface into high-dimension latent features. And then the feature disentanglement module will disentangle the latent feature into identity and age-related features. Then the identity conditional block, which combines the individualized information with time points, generates a prediction series by a decoder. By the way, our proposed framework could predict multiple cortical feature maps simultaneously. Some people may wonder, why don't we directly use the latent feature for following generation? As the brain develops over time, the primary and secondary cortical faults are well established and keep relatively stable. So we suppose the identity-related features should be time invariant, and the age-related features should change over time. Therefore, we would like to decompose the latent features into two components: identity and age-related features. Besides, the contrastive learning is useful for identity-related feature disentanglement. Therefore, we then formulate the training samples into AAA units, where the first two samples are from the same individuals by a different age, and the last one is from another individual at any age. We suppose the identity-related features from a pair of same individuals should be identical, while the pair of different subjects should be dissimilar. Therefore, we apply the intensive AAA loss to encourage the disentanglement of identity-related features. And then we use the cross-entropy loss to supervise the age-related feature disentanglement. To guarantee the consistency between two trajectories, we first consider Euclidean warping distance. However, the Euclidean warping distance compares each time point separately, which cannot perfectly compare the tendency of trajectory. Therefore, we leverage the dynamic time warping algorithm for measuring the similarity between series, which computes the distance from matched series and find the optimum path. However, one strong limitation of dynamic time warping is that it cannot be differentiated, which is problematic given the gradient-based optimization in machine learning. So we use the soft dynamic time warping as longitudinally consistent loss. Gamma here is the smooth factor, where equals to 0.1. To avoid a scenario that trajectories deviate from the corresponding ground truths, and to ensure the meaningful and reliable generation of cortical surface map, we have incorporated a reconstruction loss. Note that only anchor and positive surface from the AAA units are included for reconstruction loss, since they have its corresponding ground truths. To achieve a generative model that is simultaneously more controllable and meaningful, we incorporated additional constraints, which is cycle consistent loss, to ensure the backward mapping process during the training of the decoder. And since the cycle consistent loss do not require paired ground truths like reconstruction loss, all samples in triplet were included for calculating the cycle consistent loss. So here's the full objective losses and training process. To evaluate, we used 437 cortical surface from 209 subjects from the BCP dataset. All subjects were split into training and testing set, and a 5-fold cross-validation were used for tuning the parameters. All the cortical surface were processed using IB2. We used 4 cortical property maps, including cortical thickness, sulcal depth, surface area, and myelin content, as our input channels. We use dynamic time warping distance for validation of longitudinal consistency, the mean absolute error and Pearson correlation coefficient as the evaluation metrics for morphology prediction. We benchmark our framework against 2 spherical neural networks, the CSUNet and the DITSAA. To evaluate if the longitudinal consistency is successfully preserved, we first illustrated the individual level trajectories predicted by different inputs. For individual 1, there are 5 time points. Each color of dashed line denotes a predict trajectory from different time point. We can clearly find that the CSUNet show the same value at any age, indicating a tendency towards average results and overlooking the individualized patterns. The DITSAA preserved more individualized patterns, but significant gaps were observed between results based on different inputs. In contrast, our method demonstrates strong consistency among themselves and closely align with the ground truths. Other individuals also have similar patterns. We also calculate the average distance in terms of DTW. The lower, the better. Our proposed method had the lowest distance between different predicted trajectories. Then we validated on individualized prediction. The visualized average error maps show that our proposed methods have superior results to other competing methods with lower errors. The quantitative results also show superior performance of proposed methods to other networks. In conclusion, we propose a flexible framework for individualized prediction of complete longitudinal developmental trajectory, and we could predict multiple cortical features simultaneously. Besides, we reinforce the longitudinal consistency of different inputs and to decrease the ambiguity in practical scenarios. Moreover, the predicted surface mass could be used for data augmentation in training various deep learning methods. That's all. Thanks for your listening. For more information, you can check our website.